Insertion sort is one of the most straightforward and intuitive sorting algorithms. In this tutorial, we will go over the intuition behind that sorting algorithm, after which we will implement it in Python and simulate the implementation on an example array. In the end, we will discuss some cases where insertion sort can actually perform better than some faster sorting algorithms like merge sort or radix sort. To understand the intuition behind the insertion sort algorithm, imagine that you hold several cards in your hand that are sorted in increasing order. Now you get another card and would like to insert it in the set of cards you're holding so that the cards stay in increasing order. So having this set of cards and the new card, we would start from the last card and start comparing the value of the new card to the value of the current card. As long as the value of the new card is smaller than the current one, we will move it to the left. And as soon as we get to a point where the value of the new card is larger than the current one, we will know that we've found the correct place for our new card. This is the basic intuition behind the insertion sort algorithm. Having a sorted array, we start by adding the new value at the very end of the array and then shift all the larger elements to the right, after which the new value finds its correct place. Let's look at how the insertion sort algorithm would work on an unsorted array of cards. At first, we only hold the first element of the array as a card in our hand. That way, when the second element arrives, we can compare those two values and place the second element in its correct place. So we will be holding two sorted elements in our hand at this point. After that, the third element will arrive and we will start comparing it to the cards in our hand, starting from the last one and move to the left to find its correct place. The same thing will happen for the fourth element and we will move it to the left until we find its place. Finally, the fifth element will find its place by comparing to all the elements from right to left until we find the first element that's smaller than the new card. This information is already sufficient to implement the insertion sort algorithm. You can pause the video and try to implement the algorithm yourself. Okay, to implement the algorithm, we'll start by iterating over the index of the new element that we want to insert. The elements to the left of I are already sorted, so we will assume they are the cards that we already hold in our hands. That's why we'll start from 1, assuming that the element at index 0 is already in our hands. The cards to the right of I are the unsorted cards that haven't arrived yet, so we will ignore them for now. This way, we will try to insert the card at index I into our hand of cards that are to the left of I. As long as the new card is smaller than the previous element, we will swap them and decrease the pointer to move one element to the left. This way, when the while loop finishes its execution, the new element will appear in its correct place. Believe it or not, with these 5 lines of code, we have implemented the whole insertion sort algorithm. To get a better intuition of the insertion sort algorithm, let's simulate the implementation on an example array. So having this array, we'd like to sort it in increasing order. We'll start with I equals to 1, assuming that the first element is already in our hands and we'd like to find the correct place for the element at index 1. We will compare 12 and 3, and as 3 is smaller than 12, we will swap them and decrease the value of j. As j is equal to 0 now, we will break the while loop, and this way we will have 2 sorted cards in our hands. We will then move on to I equals to 2. We will compare 5 and 12. As 5 is smaller than 12, we will swap them. After that, we will compare 5 and 3. As 5 is not smaller, we will stop the while loop. During the next step, we will compare 9 and 12. As 9 is smaller, we will swap them. After that, we will compare 9 and 5. As 9 is not smaller, we will stop the while loop. In the next iteration, we will start by comparing 4 and 12. As 4 is smaller, we will swap them. After which, we will compare 4 and 9. As 4 is smaller, we will swap them again. Moving forward, we will compare 4 and 5. As 4 is smaller, we will swap 4 and 5. We will finally compare 4 and 3, and as 4 is not smaller than 3, we will stop the while loop. Notice that we already have 5 sorted cards in our hands and 2 more to go. We will compare 1 and 12. As 1 is smaller, we will swap them. After that, we will compare 1 and 9. As 1 is smaller, we will swap them again. We will then swap 1 and 5, after which we will swap 1 and 4, and finally we will swap 1 and 3. At this point, the value of j will be 0, and we will stop the loop. Next, we will compare 7 and 12. As 7 is smaller, we will swap them, after which we will compare 7 and 9 and swap them. As 7 is not smaller than 5, we will stop the while loop. This way, we will have the full array sorted in increasing order. Okay, let's now analyze the time complexity for the insertion sort algorithm. We iterate over all the elements one by one, and for each of those, we find their correct place by looping through the array from right to left. So in the outer loop, we perform n-1 operations, and in the inner loop, the number of operations can be different depending on the initial order of the array. In the worst case scenario, where all the elements of the array are sorted in reverse order, the inner loop would perform all of n operations for each element, as we would need to bring each element to the very start of the array on each iteration. That way, the total time complexity of the insertion sort algorithm would be of n squared. Many people say that the insertion sort algorithm is a very slow sorting algorithm, but in certain cases it can actually be way faster than other sorting algorithms like merge sort or radix sort, which are considered to be way faster on paper. Let's imagine having a very large array where all the elements are almost in their correct places, meaning they're at most 3 locations away from their final destination. Well, in that case, the insertion sort algorithm would be way faster than merge sort or radix sort. With insertion sort, we would perform at most 3 times n operations, which expressed with a big O notation would be O of n operations. While with merge sort, we would perform O of n log n operations, which is significantly slower than the insertion sort for this specific case. This highlights the importance of choosing the right tool for the right problem. Usually, there isn't a great algorithm that works for all scenarios. It's more common to see different algorithms that are more optimal for specific problems and use cases. And that's where it's very important to know how each algorithm works and to really understand what's actually happening under the hood. And to have a thorough understanding of how each algorithm works, one needs to aim for mastery of those algorithms, which is only possible through a lot of practice. To practice the insertion sort algorithm and many other techniques, head to Profound Academy with the link in the description and try solving several problems. So this was it for the insertion sort algorithm. Don't forget to like and subscribe to see more tutorials like this. Thanks for watching, and I will see you in the next one.